So we've built the thing, and we now know how to filter the webcam feed and squeeze out the important stuff into a text file. And now we'll learn how to turn that into this. So in this part I'll be showing you how to go from a text file with the X and Y pixel coordinates to a 3D point cloud. Things get a bit trickier at this point, but if you've followed along this far it shouldn't be a problem. So how does it work? Well, basically we set up a scene in 3D space using some key dimensions and angles relating to the scanner, the distance between the laser and the camera angle, etc. We then take those white pixel coordinates and use them to produce imaginary projection lines coming out of the camera. We then calculate where each of those lines intersect with the imaginary plane created by the line laser. At that intersection we can place a point in 3D space. We then do this for every white pixel and build up a 3D point cloud. Okay, so the only thing we need to put in the setup here is the size of the rendering window. I'm making it 1000 by 1000 pixels to make it nice and big. And we also need to make it P3D to create our 3D display. Now we need to set up our parameters. There's quite a few that need to go in here, there's about 15 different ones. And all of them are floats because they need to have decimal places. So first off we need the motor rotation, or rot-mot. This is the angle sent from the Arduino. And the camera rotation, this is how far the camera is angled inwards. Mine's set to about 35 degrees right now. We also need to convert this to radians for using later on. We don't really need the laser's rotation, but I'm sticking it in here anyway just for completeness. Also, we might want to rotate the laser later on for some reason, but for now we're just leaving it as 0. Here we need the X and Y rotation of the pixels from the camera's centre. This might sound a bit odd at the moment, but it should become clearer later on. Basically, it's the angle between the camera's centre view and those projection lines that I spoke about. And here we need to define the angle between each pixel. The specs for the webcam says that the viewing angle is 50 degrees. I'm guessing that's the width, so spread over 640 pixels. So that's 50 divided by 640, that gives us the angle per pixel. Again, it needs to be converted into radians. I'm also assuming that this is going to be the same in the Y direction. I could check this more accurately by marking points in the wall just on screen of the camera and use trigonometry to figure out the actual angles, but this is good enough. These next few ones won't really make much sense at the moment. They're just a bunch of constants needed for the equations for the pixel lines and laser plane. And the reason I'm putting them in square brackets is because that makes them vectors, so I can put multiple values in a row just in the one variable. This is because the calculations are done over and over again for every single pixel in a frame, and then this is done again for every single motor angle. We also need a temporary holding space for the X, Y and Z coordinates for the data point in space. And then we need a final storing place for each 3D point in space. For this we'll use 3 separate vectors, each for X, Y and Z. So for example, the first point we calculate will be stored with its X coordinate in draw point X in element 0, and the same for draw point Y and Z. It's stored in element 0 because that's the first element or space in the vector. So we'll end up with 3 huge vectors holding parts of every data point. And we need to create an integer k and set it to 0. Like before, this is just for counting something within the loop. And by the way, if you're not familiar with processing's 3D environment, then please check out Daniel Schiffman's tutorials. They're very good and taught me most of what I know now in processing. Okay, so to start with in the main loop, we're just going to set the background to black. And then we're going to add the function perspective. This is basically just to set the clipping planes closer to the camera so it doesn't cut anything off from the image. And then we can add some lines to give us an X, Y and Z reference. This comes in really handy later on when you're trying to find out why your model's inside out and back to front. So here I'll set the colour to red and make a line starting from the origin and extending to 50 units along the x-axis. Then I'll do a green one for y and a blue one for z. Here I'll set up the camera in the scene that we're looking through. This has nothing to do with the webcam. Just to warn you though, the camera controls and processing are a nightmare to work with. It is not like a 3D program like Blender where it's made all easy and intuitive. You need to program it yourself from something that's much more raw. So there's 9 input parameters. The top 3 are the camera's position. The next 3 are the position of what it's looking at. And the last 3 are just 0, 1 or -1, and they determine which way is up for the camera. For the camera's position, I'm going to do something a little bit fancy. I'll use the mouse's X position on the screen to rotate the camera about the centre using sine and cosine. This is really handy because it gives you the kind of turntable effect you get in some 3D programs. You can mess about with these and see what works well for you. So now we're jumping into the part where we grab the text file and make it into the point cloud. We start by putting the entire thing in an if statement that only works if we press a key on the keyboard. Any key should do it. I'm doing this so that all the data points are only calculated once when I press a button, so they're not constantly recalculating. So within this statement, the first thing we need to do is import the text file. We do this by saving it to a string vector. I'm not sure why it has to be a vector, seeing as it's all in the one string. And all only contained within the first element of vector myString, but it just does. It won't run as a single string. So we use load strings with whatever you called your text file. Also, the text file has to be located within this sketches folder. So you have to copy it over from the last processing sketches folder that we just did. Next we need to create empty vectors for the draw point x, y and z floats. This is just to initialize them before we put anything into them. So we know how big they all need to be from the text file, because there will be as many data points as there are white pixels that we captured during the last processing sketch. So we choose the number of empty vector elements by typing new float and then using square brackets to put in the number that we want. So here we use a basic function called split tokens. This splits up that massive string that we just saved by using a specified character within it. So we separated all our x and y coordinates with a comma, so let's use that. And now we can count the number of elements in that temporarily saved string vector using dot length. So for example, if there were 100 white pixels, this would come out as 200 because there's x and y coordinates, so we need to divide that number by 2. So now this is just the right number of empty elements to save those 100 data points. When we use split tokens there, we didn't actually do anything to the myString string. We just used them in a calculation. Now we are actually going to use them to split it up, but in a different way. We're going to split it up using the semicolon. This will allow us to split up that massive string into smaller strings that each contain a single frame from the camera with a load of white pixel coordinates in each. And here we need to equal k to 0, so it's reset just before we go into the next loop. This next section is where all of the calculations are going to be done. It uses a for loop within a for loop. The outside for loop deals with the individual frames coming from the camera, and the inner for loop picks apart the individual white pixels in each frame and does some calculations with them. So this outer for loop will count the number of frames that are in the text file. And remember that the vector string myString is now split up into the individual frames. So the number of loops is just the number of elements that's in myString. When we get into this loop, we want to create another string called partString. And we'll use split tokens again, but with the comma separating the values. This is so we now have the x and y coordinates of all the white pixels, as well as the motor angle at the very start, neatly separated in the string vector so we can access them easily. Also, notice here that I'm only doing this to myString element I. That's because in this outer loop we're only looking at one frame at a time. After it's looped, we'll look at the next one until they're all done. Next we can find the motor angle and save it temporarily to rotmot. This is easy because it's the first thing in that string vector we just made. Remember, the first element's actually 0, and we need to convert it from a string to a float. Next, we're going to look at a new function called pushMatrix. This is used to create a new local coordinate system in 3D space after a 3D transformation. PullMatrix is the counterpart, which puts it back to the normal global coordinate system. Anything within those two statements will have their coordinates shifted to a local system. Check out Processing's website for a better description of this if you need to. So within this pushMatrix, we need to rotate the y-axis by the angle of the motor. I'm using minus because my stepper motor actually rotates the wrong way. This doesn't really matter, just change it if you need to. And remember to convert it to radians as well. So this rotation is now going to affect everything within the pushMatrix, and we can add more transformations on top of this. We now put in another pushMatrix, so one within another, to translate our local coordinates to the laser. So we translate by minus 19 centimeters in the x-axis and up 2 centimeters in the y-axis. So this means that our coordinate system's origin is now inside the laser, so we can easily make a plane here to simulate the laser line. I'm also going to add another rotate transformation in the y-axis to match the rotation of the laser, but remember that we don't actually need this because the angle of the laser is always 0, so it's facing straight forward. I've just put this in here for completeness. Okay, so now we'll produce an equation for the plane that represents the line laser. To make the equation, we need 2 points that make a line perpendicular to the plane, and this will be our normal vector. This is easy enough to do using model x, model y, and model z functions. These take transform coordinates, so those translations and rotations that we did, and turn them into global coordinates. So right now our new local origin is rotated by some angle and shoved over to the side by 19 centimeters and up by 2 centimeters. If the motor angle was 0, then it would be easy to figure out the coordinates of where we are now. It's just x is minus 19, y is 2, and z is 0. But if the motor changes its angle, it becomes a lot trickier to calculate this. Luckily, this function does that all for us. So we want to make a normal vector line coming from the side of the plane. So first we make a point, call it C, at local coordinates 0, 0, 0. Using the model x, y, and z function, this gives us its actual global coordinates. And then you do it again for the end of the line. So we want to translate it in the x direction by 10. So you make another data point there and call it D. So that's just made a line, or normal vector, going from the laser's centre to 10 centimeters in the x direction, perpendicular to the plane. So now we need to make an equation for the line CD by subtracting C from D for each x, y, and z coordinate. We can then make the plane equation using this. We can then use popMatrix to come out of the transformations that took us to the laser's position. But we're still going to use the coordinate system for the motor's rotation, so the motor's angle still affects what we're doing. Now we're jumping into the inner for loop that calculates all of the imaginary pixel lines coming from the camera. This loop also calculates the point of intersection between all the pixel lines and the laser plane. So for this one, we want to make a loop that repeats just enough times to account for every white pixel in each frame. To do that, we need to make it as long as that string part vector that we made a minute ago, because this is all the coordinates for the current frame in it. So make the for loop, and this time use j as the counter, because we're already running a loop that's using I. Also, we need to start it at 1 instead of 0. This is because element 0 is in the string part is the motor angle, and we already used that and we don't care about it anymore. We just want the x and y pixel coordinates. We're also going to increment j by 2 in each loop. This is because we're using 2 bits of information from the string part each time, the x and y coordinate. So if we increment it by 2 every time, we can say the x coordinate is just element j, and the y coordinate is in element j plus 1. Now we need to think about the imaginary pixel projection lines coming from the camera. To create them, we first need to see what angle they're going to be fired out of the camera at. We need both the X and Y angles from the camera's centre. We know the angle between each pixel from the camera's centre from the calculation we did at the beginning and saved it into pix angle X and Y. So with that in mind, we can find the angle of any white pixel from the camera's centre by multiplying that angle by the number of pixels it is from the centre. In this loop, we only do one pixel at a time, so imagine that there's only a single white pixel in the webcam frame to make it a bit easier. So to get the pixel's rotation in the X direction from the centre, we take the string part J, remember to convert it to a float as well, and take away 320 from it. This centres it to a screen that is 640 pixels wide. We then multiply it by the pixel angle. So, for example, if there was a white pixel at 0.00, so at the top left hand corner of the screen, then it would be 320 times pix angle, which is about 0.078 degrees. This gives us minus 25 degrees, which is perfect, because it's half of our 50-degree total viewing angle. This is repeated in the y direction, but this time it's 240 minus the y coordinate. And remember that the y coordinate here is j plus 1. We then go into another push matrix, which takes us from the motor shaft with the motor's rotation transformation along the arm of the scanner to the webcam. So to do this, we need to translate along the x-axis by 18 centimeters and up by 4.5 centimeters on the y-axis. This takes us to the camera's center. We then use the camera's angle to translate in the y-axis. And then rotating the x-axis using the angle that we just got for rot pix y. So this is changing the up and down angle, which is done by rotating the x-axis. And finally we need to rotate in the y-axis again, which rotates left and right using the rot pix x. Right, so now our local coordinate system is centered right inside the camera's position, with its z-axis pointing out the lens and onto the laser plane, exactly where the camera can see that white pixel. Hopefully it's starting to make a little bit of sense now. So imagine that you're projecting the white pixel from the camera onto the plane created by the laser. Okay, so now we need to make an equation for that projection line. We've done this for part of the plane equation that we just did. So again, using the model x, y and z functions, we make two single points, one at the camera's centre and one at some distance out along the z-axis. So call these 2 points A and B. Then get the equation of the line AB by taking AX away from BX and AY away from BY, etc. We then need to go back to the motor shaft angle again, still with the rotation transformation with pop matrix. So for this next part, we need to take the x, y and z components of the line equation. We then need to substitute them into the x, y and z components for the plane equation. Then we need to rearrange this for t and put it back into the line equation. This then gives us the x, y and z coordinates of where the two intersect. So here are the bits that you need. So here's that big equation rearranged for t. And here are the final equations we need to get our x, y and z coordinates of a single point, where A is the coordinates at the camera's centre and AB is the equation of the projection line, and t is that big equation above that's substituted in. So now that we finally have our three coordinates, we can now plop them into these three vectors that I mentioned right at the beginning. They're huge vectors that contain the positions for all data points in the point cloud. And here we increment k for the next loop. K just keeps track of how many data points there are in total, so they can be easily put into their proper place within the drawpoint vectors. We then close the inner for loop and pop the matrix for the last time, which takes us right back to the original global coordinates, so there's no more transformations manipulating what we're doing anymore. So we can now close off the outer for loop and the key pressed function. And finally, we can make a small for loop that actually draws all the points that we've just made into the render window so we can see them. Keep in mind that we only want to draw these points if they've actually been calculated, so we aren't trying to make it draw something that doesn't exist. So we only do this if k is more than 0. So now we can make our last for loop. So because this loop repeats once for every data point, we need to make it run that many times. So we use the number of elements in drawpoint x vector to determine its length. So we want the loop to repeat once for every single dot that is made in 3D space. So set the stroke to 255, this will make the dots white, and then make a point for each x, y and z coordinate. And then close off the for loop, the if statement and the main loop. And that's it. I hope you enjoyed the series and get a chance to build this for yourself. If you do build it and make a video or something, I'd be really grateful if you mentioned my tutorials. If you enjoyed this, then please leave a like or whatever, and if you really liked it, you can head over to my Intructables version of it and vote for me in the full spectrum competition. I have some ideas for taking this project further, which I'm really excited about, but I'm afraid I'm not going to tell any of you because I only trust myself and my cats. So stay tuned to find out more about them. Happy scanning. Catch you later. So there's no more transformations